All right, so chapter 2, we start with something called atoms first, where we're going to learn about what atoms are and why our textbook goes in the order of material that it does. So Democritus was the first person who called something an atom. He said that the smallest piece of matter is indivisible. We're going to call it atomos. Atomos means uncuttable. You can't separate it. It's too small to be separated. And nobody believed Democritus. Nobody believed him until we were able to do experiments and find out that he was right, that there is a type of a piece of matter that you can't get any smaller, except for protons and neutrons and electrons, but we'll get there. He was right, but nobody believed him. And back then, science was not actually based on experiments. They didn't use the scientific method. They made observations, and if you were more popular, people believed you, which is what happened with Aristotle. Aristotle said that matter is made up of 4 elements: air, water, fire, and earth. Whereas that is the case in Avatar: The Last Airbender, it's not the case in the real world. So unfortunately, Aristotle was more popular than Democritus, so he was believed for 2,000 years. So people believed him up until like the 1800s, 1800s, because he was more popular. So people believed that matter was made up of 4 elements: air, water, fire, and earth, and nothing else. They didn't know about atoms. They didn't know about the periodic table of elements. They just believed him, and this was based on alchemy, where you could convert between elements, like you could make gold out of different metals from the earth. That was what people believed back then before they started doing experiments. Crazy, right? All right, but now that we know, now that we've started to do experiments, which we're going to see in just a second, we know that elements are made up of atoms, and that atoms of one element are different from atoms of another element. Might sound simple, but they didn't know this then. They didn't know what made up different elements. Like I said, they thought matter was made up of air, fire, water, and earth. But now we know that it's not. Atoms of a single element are identical. This is the first hypothesis of Dalton's atomic theory. The rest of Dalton's atomic theory we'll get to in later chapters, but it basically describes how compounds are formed using a fixed whole number ratio of one element to another. Like H2O down here, water, is always 2 parts hydrogen, H2, and 1 part oxygen. That's another part of Dalton's atomic theory that we'll get to later, as well as the fact that chemical reactions are a rearrangement of the bonding of the atoms. And the atoms themselves are still the same. The atoms of hydrogen do not change, just what they're attached to. So hydrogen, instead of being attached to itself, becomes attached to oxygen in a water molecule. That is a chemical reaction, but the atoms themselves are unchanged. But the first part is what we need to know right now, that elements are made up of one type of atom, and they are all the same in that type of element. All right, so I'm not going to play this video for you guys, but you should watch it. So these videos are linked in your textbook. So if it says there's a video, don't just skip over it. Click on that link and watch the video. It's really informative and gives you a new way of thinking about things rather than just reading your textbook. So that video was about something called a cathode tube, or cathode rays. And that was what was used by Thomson, J.J. Thomson, when he found electrons. So we found out that there are actually smaller things than atoms. They are subatomic particles. called electrons, protons, and neutrons. The first one that was discovered were electrons. We set up something called a cathode ray, which is a beam of energy, which is shot from the negatively charged end of our tube to the positively charged end of our tube called the anode. And if we let a little hole in our anode, that beam of particles, it's actually a beam of particles, they didn't really know that at the time, but that beam is shot through this tube and shows up on a fluorescent screen. So you can't really see anything in the beam. We can't see the individual atoms or the parts of the atoms, but we can shoot it at a fluorescent screen in order to see it. It'll make a mark on the fluorescent screen. So what J.J. Thomson did was he used this cathode ray tube and he fired this cathode ray. And what he saw was that when there is the presence of an electric field, so the electric field is denoted by these plates where there's a positive blue plate and a negative orange plate. And there's also a magnet with a north and south pole. So with the electric field and the magnetic field, he was able to look at how this beam of particles is deflected or attracted to these different electric and magnetic fields. And doing so, he found out that electrons are negatively charged. So he shot this beam of negatively charged particles through this system, and they were attracted to the positive part of the electric field and ended up at point A, or they were deflected by the magnetic field and deflected to point C. When you have both the electric field and the magnetic field in balance, we could get them to go straight through to point B. So I would watch that video. It gives a really good explanation of this whole system. But basically, using the electric field and the magnetic field, as well as our different equations about force, force related to electric fields, force related to magnetic fields, and force related to mass and acceleration. Those three mathematical relationships combined are able to tell us that the charge to mass ratio of an electron is 1.76 times 10 to the 8th coulombs per gram. Coulombs is a measure of charge. So electrons are negatively charged. So it's the measure of the charge of the electron as a ratio of the electron's mass. So with these sets of equations, we can only get this ratio. We can't determine the charge itself or the mass itself, but we can determine how the charge and mass are related. And that was a huge thing that we found out back then, what the charge to mass ratio of an electron was. First of all, it was huge just to find out that there were things smaller than atoms, that we could see that the atom breaks down into these negatively charged things when we use electric and magnetic fields. But we know that atoms are not overall negative. They are neutral, or they would have very different properties. So that means there must be a cloud of positive charge in an atom to counteract the negative charges. So Thomson described the structure of an atom using this, what he called the plum pudding model, where it's a sea of electrons and positive charges spread kind of uniformly throughout the atom. So kind of like raisins in this plum pudding, which is kind of like a cake. So we've got our positive charges and our negative charges spread throughout. And then we went on further to be able to find the actual charge and mass of our electron using this oil drop experiment, which is video 2.2, which you should watch as well. There's a link to it in your textbook. Make sure you watch the video. I'm not going to show it to you now. All right, so this experiment was developed by a guy named Millikan. So Millikan did this experiment to find the charge and mass of an electron. So first of all, he had this oil that he sprayed in a really fine mist into a chamber. And this chamber has a tiny, tiny pinhole for individual droplets to go through. So he made the pinhole small enough so only one droplet at a time can go through to the bottom of the chamber. Then he used X-rays to produce the charge on an oil droplet. So he shot some radiation into this chamber and charged the oil droplet. So he gave it a negative charge using electrons. And on either side of this lower part of the chamber, we have an electric field caused by two differently charged plates. So what happens is that we gave these oil droplets a negative charge, and then we can balance those droplets. We can actually use the electric field to repel the droplets with enough force to balance out the force of gravity. So these droplets would be dropping to the bottom based on gravity, based on their mass, but we can stop them and make them levitate by using just the right electric field, just the right charge to keep them suspended between the positive and negative plates. By doing that, we can balance out the mass and the charge. So we have the mass, which comes into play with the gravity, with the field, the force of gravity. So that is causing the particle to be pulled down, but we can balance that force using our electric field, so we can balance out the mass and the charge. And once we have one or the other, we can use our mass to charge or charge to mass ratio from Thomson's experiments to determine the individual charge and mass, respectively, of the electron. So this experiment was used to find the charge on the electron, which is negative 1.6 times 10 to the negative 19th coulombs. Really, really tiny, 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 tiny charge. But that makes sense because the electrons themselves are really, 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 really tiny. So they shouldn't have a huge effect if they're really tiny themselves. The mass of the electron was determined to be 9.11 times 10 to the negative 28th grams. You guys don't really need to remember these numbers, but you're going to need to remember kind of how they relate to the charge and the mass for our other subatomic particles, protons and neutrons, okay? Cool. All right, so I used the word radiation and X-rays before. So let's talk a little bit about those. There were two guys, two main people who studied radiation, and that was Rontgen and Becquerel. I don't know if I'm pronouncing their names right. Rontgen was studying cathode rays, and he was shooting them at glass and metal. And when he did that, it caused the glass or the metal to emit X-rays. He called them X-rays. Don't know why, but that's what he called them, and that's what we call them now. It caused the material, the glass or the metal, to fluoresce. So the glass or the metal gave off light. So it's kind of like turning on a light bulb. It got all this energy from seemingly nowhere, but from the cathode rays. The X-rays were not deflected by magnetic or electric fields, so unlike the electrons, they didn't move when we had a magnetic or an electric field nearby. So that means the X-rays do not consist of charged particles. X-rays are neutral, neutral charge. And then Becquerel, he was using some uranium. He put some uranium near a photographic plate that had no exposure to light. So there was no light that should cause these photographic plates to darken, but the uranium itself caused the photographic plates to darken. So this was another type of radiation, and they knew that this radiation was not made of charged particles either, because again, it was not deflected by magnetic or electric fields. The spontaneous emission of radiation, like these two types of radiation, are called radioactivity. So any type of material that spontaneously emits radiation, I should apologize, not like X-rays. X-rays were produced when we used cathode rays. Uranium, there's no addition of energy. There's no addition of negative or positively charged particles. The uranium causes this to happen on its own. That is a spontaneous emission of radiation. So uranium is what we call radioactive. We don't add any energy, any types of beams of particles to uranium. It just emits radiation on its own. And the three different types of radioactivity or radioactive particles are alpha rays or alpha particles, beta rays, beta particles, or gamma rays. So alpha particles are positively charged. They are actually protons, which we'll discuss on the next slide. Beta particles are electrons. They are negatively charged. We know that by how they react in an electric field, as shown in this picture down here. And gamma rays are very high energy. They're higher energy than X-rays, actually. But they don't have any charge. They go straight through. They are not affected by the magnetic or electric fields. And down here we can see how a lead block, we use the lead to protect ourselves from the radiation. The radioactive substance like uranium is in this lead block and it's giving off radiation. It's radioactive. It's giving off spontaneous radiation, which we can control using electrically charged plates to see three different types of radioactive particles: beta rays, gamma rays, and alpha rays. All right, so now that we know about beta rays, alpha rays, and gamma rays, we can talk a little bit about the proton and the neutron. So protons are positively charged. So if you remember back to our cathode ray tube, we shot our cathode ray from the cathode, the negatively charged plate, to the anode, the positively charged plate. The beam of particles was attracted to the positively charged plate because it was a beam of negatively charged particles. Now we're doing the opposite. We're shooting our beam of particles from the anode to the cathode. So the anode, which is positively charged, is shooting a beam of particles or a beam of energy through a gas to the other side. So it's going through to the negatively charged plate. So now you can assume, and this is correct, that the beam that's going from the positive end to the negative end, it's attracted to the negative end, is a beam of positive particles. Those are our protons. The positively charged particle ends up on this side of the negatively charged plate, whereas the electron ends up on this side of the negatively charged plate. It is deflected. It is not attracted to the negative plate because it's negative. The positively charged one ends up going through because it is attracted to the negative plate. So this was done by a guy named Wien. Probably not pronouncing that right because he's German, but the protons he found were positively charged. So we have something that is the exact same charge as an electron, but positive. And someone named Chadwick later found the neutron. And sometime in between there, we found the mass of the proton, which is 18,000 times bigger than electrons. We'll get to that on the next slide. Neutrons were found even later, and those were found because the mass of a proton does not make up the whole mass of an atom. And that was weird. We didn't know why. So we had to find out that there was something else in our atom, not just electrons and protons. We had something else contributing mass, and that was the neutron. And that was found by a guy named Chadwick. All right, so let's talk about those masses. So Rutherford was a student of Thomson, actually, and he found out that atoms are mostly empty space. There's a dense positively charged nucleus in the middle of an atom. And we know now that that positively charged nucleus is made up of both protons and neutrons. So how did he find that out? So this is a diagram of his experiment. He used a radioactive source, and that source produced alpha particles. So we must have used something else to deflect the negatively charged particles. So now we're only looking at alpha particles, which are protons, are positively charged protons. This beam of alpha particles is shot into a piece of gold foil, and we're surrounded with a luminescent screen so that we can see where the particles bounce off. So that means we can't see these alpha particles, but we want to know where they end up after they hit the gold foil. So we need something that fluoresces when the positive particles hit them. And that's why we have this screen that goes all the way around. So when those alpha particles, when those protons hit the gold foil, some of them went all the way through, which is kind of what we expected if our if our atoms were mostly empty space with uniformly distributed positive and negative charges. So the Thomson model over here, our plum pudding model on the left, has positive and negatively charged subatomic particles. So positive is the negative, purple is the negative particle here, and the bluish color is our sea of positive charge. So we knew about electrons, and we just thought that the protons were a sea of positive charge. So we thought that the alpha particles go all the way through because the sea of positive charges was uniformly spread out. So it wasn't that electrically charged or electrically reflective in any one location because the positive charge was uniformly spread throughout. But what happened is that sometimes Rutherford saw that some of these alpha particles were being deflected straight back from where the gold foil was. They were not going through at all. They were bouncing off, which was only the case when he considered this other model of the atom. So this Rutherford model of the atom is more accurate, where the positive charge is still blue, but in this case, the positive charge is a dense nucleus in the middle of the atom. So when our positive charge is a dense nucleus in the middle of the atom, that means that if a positive particle comes towards it, it's going to bounce off because there's a whole lot of positive charge in one location instead of spread throughout the atom like we thought it was. So that's how they found out that's how they found the nucleus and determined that the nucleus is positively charged. All right, so just to wrap up here then, this is a more accurate version of an atomic model where we have the nucleus made up of protons and neutrons in the center of our atom, and our atom, the rest of our atom, is called the electron cloud. We know that that's where the negative charge is because most of our alpha particles went straight through. which means they weren't deflected by anything, which means that's where our electrons are. So the electron cloud actually makes up so much more of the area of the atom. So this electron cloud is actually not drawn to scale. For your reference, if you think about Kyle field as the atom, the nucleus of the atom would be if you put a marble in the middle of center field of in the middle of the football field. So that is a tiny, tiny marble in the giant expanse that is Kyle field. So the electron cloud is 10,000 times the diameter of the nucleus. The nucleus is the atom itself is about 100 picometers in size on average. It depends on the type of element for sure. And the nucleus is typically 0.01 picometers. So picometers is one of our units of distance that we use to measure things on the atomic scale. And pico is one of the prefixes. You guys don't need to memorize that one, but it's one of our metric prefixes. All right, and then this is a table that summarizes that stuff for you. The electron is tiny. It is almost 2,000 times smaller in mass than the proton and the neutron. And we also have its mass in atomic mass units, which are basically based on the size of a proton or a neutron. But the electron is negatively charged, and this is its charge in coulombs. But relatively speaking, it's a -1 charge, whereas the proton is a +1 charge, and a neutron is neutral and has 0 charge. The mass of the proton and the neutron are pretty close. The neutron's a little bit bigger. But even though they are almost 2,000 times bigger than the electron in mass, when they're in the atom, they take up 10,000 times less space. So the electrons are really, really small, but they're really, really spread out in our atom. And then down here is just a little quote from Rutherford, which was really interesting. It's as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So that's describing the density of the nucleus because of the deflection of the alpha particles or the protons when we shot them at the atom. They bounced off of the nucleus, even though the nucleus is so much smaller than the size of the atom itself. All right, and then here's just, oh, sorry, that's it. All right, and that's it.